Hello everyone, I'm Eishi Arima from University of Tokyo. I'm very honored to have a chance to make a presentation in such a nice conference and virtually in Frankfurt. This talk is about the power management for hybrid memory-based systems, especially for high-performance computing systems and supercomputers. This work is a kind of collaborative research between TU Munich and University of Tokyo, and accomplished while I was in Munich for many months. Okay, let's get started. Okay, here is a summary of this talk. Our focus is component-wise power management, especially power capping on high-performance computing nodes, especially based on hybrid main memories. And our motivation is optimal power allocation to component highly depends on the data size of application. This is basically because a large but slow memory is more frequently accessed when we scale the problem size of the application, which changes the bottleneck. And the proposal here is FPCAP, footprint-aware power capping. We firstly formulate the power allocation problem and present an empirical performance model to solve it. And we provide a profile-based software framework that consists of efficient calibration method and also power allocation algorithm. And the result is quite promising. Near optimal power allocation can be achieved. And here is the outline of this talk. Let me talk firstly about the technology trends. The power consumption is a major performance limit in supercomputers, and it's a major problem, especially for exascale systems and near exascale systems. It's more than 30 megawatt, which is larger than the output of some power plants, such as solar power plant and oil power plant in Japan. And if we look at data centers, their power consumption is also a problem. In US case, the total data center power consumption is over 100 megawatt, which is equal to the 34 giant power plant. So the sophisticated power management for large-scale system is a must. And usually hierarchical power management is used for large-scale systems that consist of two parts. One is power scheduler that tries to optimize the power budget allocation to compute nodes. And on each compute node, they try to optimize, exploit the allocated power budget. Usually power capping, which set a power limit to each target component, and also power shifting are used. Power shifting is a concept shifting power between different kinds of components. And our focus is on the local power control. And if we look at the compute nodes, the architecture is changing rapidly, in particular in terms of memory, thanks to new emerging memory devices. One is HBM, 3D stacked DRAMs, and also the other one is NVRAMs. They have trade-offs in terms of performance and capacity. Due to this trade-off, hybrid main memory architecture is a promising design choice and becoming more and more popular. They are a prominent target of this work. And this study targets power management for these emerging hybrid memory-based compute nodes. And then next, I'm going to talk about the motivation and the approach. The basic approach in power capping is identifying the performance bottleneck component and try to allocate more power budget to it. This is because bottleneck component limits application performance and need more power performance. And the performance of a component increases if we allocate more power budget. So assuming we have 5 power budgets and try to distribute them to CPU memory. In case of CPU bottleneck, we should allocate more power budget to CPU. On the other hand, in memory bottleneck case, we should allocate more power on memory. However, the performance bottleneck component changes in accordance with the data footprint size on the hybrid memory-based systems. And we measured that on the real system. Especially, we executed this synthetic streaming code. With it, we can scale the footprint size of application by scaling the number of elements for these arrays. And also we can scale the arithmetic intensity by changing the number of multiplication. And that is executed on this hybrid memory system. The memory consists of DRAM and NVRAM. And we gained this roofline plots. The horizontal axis shows the arithmetic intensity, and the vertical axis shows the performance gigaflops. And smaller arithmetic intensity means memory intensity, and higher means CPU intensive application. And the horizontal line shows the performance limit by CPU, and the slope line shows the performance limit by memory. And if we use larger program on this system, the slope line goes down like this way. This is basically because slow but large non-volatile memories is more frequently accessed when we use larger data. And in case of CPU intensive application, if the data size, footprint size is smaller than like 64 GB, then the CPU is a bottleneck. But if we scale it to such as 512 GB, then the non-volatile memory is a bottleneck. On the other hand, if we use memory intensive application, the DRAM is a bottleneck when the data footprint size is small. But if we scale it to like 512 GB, then the non-volatile memory becomes the performance bottleneck. And we should consider this bottleneck shifting phenomenon when trying to optimize the power cap allocations. And here is our core concept called FPCAP, footprint area power capping, and illustrated here. One input is, of course, application code, and we converted the feature parameter, application features, to optimize the power allocation. And also, we explicitly consider the data footprint size because the optimal power allocation highly depends on it, on this system. And given total power budget of the node, we try to optimize the power capping. The question is, how much would be the potential impact? And we tested that on a real system. Especially, we measured the performance for all the power cap combinations under the constraint of this. So the total power cap is set at 260 watt, and we tested for two different types of problem. One is small, the data size fits within the small memory DRAM, and large problem, the data doesn't fit, and a large portion of the data is served from the large memory, here, non-volatile memory. And we used Coral benchmark plus the previously shown this synthetic code. And here is the result of mini-FE, and they are power allocation combination. And optimal settings for large problem and small problem are shown. And here is the performance result for large problem. So optimal for small isn't optimal for this large problem. And we can see the significant gap here. On the other hand, optimal for large problem isn't optimal at all for this small problem. And the performance degradation is significant. And we also show the geometric mean across all the workloads. And for small problem, optimal large doesn't work. And also for large problem, right figure, optimal for small doesn't work well. So clearly, the gap is clear, big, and we need to think about the FPCAP. And non-footprint aware approach could cause significant slowdown. So the next is about the formulation and modeling. And here is the overall workflow. So given application kernel plus the inputs for application and also the total power budget, we firstly select feature parameters like this way. Some of the feature parameters are from profile, and the others are obtained at runtime, such as footprint size. And given those inputs, our model and algorithm tries to optimize the power allocation. Here is a mathematical profile definition. Given kernel plus inputs vector and total power budget, we try to maximize the given objective function under power constraint. And here is the objective function used in our study, performance over power efficiency. And power efficiency is performance divided by the total power. And here is the performance model. We consider widely used linear regression model like this way. So that is actually the inner product of coefficient vector and the basis function, that is a function feature parameters. The details will be provided later. And we need to calibrate, determine the coefficient vector for all the possible power combinations. Here, to do so, we measure the pair of performance and feature parameters and apply the regression analysis at this square method. And then next, I'm going to talk about system design. And so this is a kind of kernel level power allocation optimization. Looks similar to the execution time measurement. The start power opt function tries to get the necessary feature parameters and also then optimize the power allocation based on the performance versus power evaluation. At the end of the power management, the end power opt function collects the stats of the profile feature parameters when profiler. So we need one profiler for each application. And here is the framework. So that consists of two parts. One is offline part, and the other one is online part. Offline part is basically about the calibration for the coefficients. And the online part is mainly tries to optimize power allocation to each component. And let me talk about the calibration process. So that consists of test runs, curve fitting, and then optimization. So this is about the test run. So given benchmark set, we try to test the execution for all the possible power cap settings P. So we will gain lots of profiles that contains the performance and also the feature parameters. And for each power allocation combination, we try to determine the coefficient vector by using the curve fitting, the least square method. We continue this for all the possible power allocation combinations. And then when we set all the coefficients, then we can optimize the power allocation by using this performance model. But one question arises, do we really need to test for the space of power combination to set the coefficient vector for all the possible power cap allocations? Well, actually, we don't want to do this. This is quite inefficient, especially when we increase the number of components in a target component in one node. Instead, we try to apply the linear interpolation approximation. This is basically just explore linearly in the space and then apply the interpolation by using this mathematical form. And more specifically, we just move the edges of the box, and calibration is applied partly, and then later we will apply the interpolation to gain all the coefficients for all the possible power allocation combinations. And here is the power allocation algorithm. So given objective function and feature parameter of the application and also the power budget of the node, we try to optimize the power allocations. The algorithm is hill climbing based. Starting from the all minimum cappings, move on to the direction that provides the highest gain step by step until reaching the boundary or the local maximum point. It's not complex at all compared to the brute force. And let me explain this with the figure. So starting from the minimal point, we test all the direction, for all the direction for the objective function, and choose the highest gain and move on to the direction. And we test again for all the direction, the objective function, and choose the highest gain and move on to the direction. And we continue this until reaching the boundary or the maximum point. And here is the evaluation. So here is the system setup. So the memory is based on the DRAM, and also the Optane SSD, and it can be used as an extension of the main memory by using the IMDT software. And the power capping is basically based on wrapper for CPU and memory one, DRAM memory. But the non-volatile memory doesn't accept the wrapper, so we emulate the power capping by scaling the PCI Express speed and detects the maximum power consumption by using the catalog spec. The details are written in our manuscript. And here is the applications and also the problem setting for small and large for each application. Okay. The next is feature parameter selection. So for profile part, floating point arithmetic intensity and also non-FP parts are considered for CPU. And for memory part, memory intensities are considered. That can be taken by, represented by last level cache misses per number of instructions. That is a frequency. And we also consider the last level cache miss rate. That is something related to the memory access pattern. And for the dynamically obtained part, we consider, of course, the footprint size. And here is the functions. The first two functions are related to CPU intensity, FP operation and non-FP operation part. And the others are related to memories, memory access intensity, memory footprint size related, and memory access pattern impact, and correlation are 3. And here's the experimental result. This is a performance comparison. The PSUM, the power budget, total power budget is fixed at 300 watt. And on average, our approach keeps around 93% of performance compared to the optimal setting for both program, large and small, which is a good number. And we also tested power efficiency on this system. The total power budget setting is the same. And we just changed the objective function. Well, this is even better. So the 96% and 95% of power efficiency can be achieved compared to the optimal for small and large programs. And we also scaled the power budget, total power budget to the node. And we tested for both small and large program and also power efficiency and performance. Regardless of problem size and objective function and total power budget setting, our method is very close to the optimal. And this is the final result, power allocation. The horizontal axis shows the power constraint, node power constraint, and the y-axis shows the breakdown of power with the estimated performance or power efficiency. Allocation order changes due to the bottleneck shifting phenomenon by scaling footprint size. And also the performance saturate area for the large program due to the NVLAN bottleneck. So that cannot fully use the allocated power budget well, because only NVLAN needs power and CPU and memory doesn't so much power because of the significant NVLAN bottleneck. And when we change the objective function from performance to power efficiency, that saturates area. Overall, the power scheduler should also consider these characteristics, because that means there are lots of unused power budget here. And the other result are the time overhead is quite negligible, and the estimated performance and power efficiency are generally close to these measures. And the conclusion, we reported power bottleneck shifting phenomenon. And based on that, we proposed the FPCAP concept and defined and formulated program and so provided the software framework and quantified the effectiveness. And those are nearly optimal. And future work, we will evaluate using more complicated real-world applications. We may revisit the section of feature parameter and basis function, but overall, that is a minor modification, and the framework should work with that. And the coordination between our framework and power scheduler will be interesting as well. And we will extension of our work to cover other kinds of systems, such as CPU plus hybrid main memory, or the other kind of application areas such as data analytics and machine learning will be also interesting to us. Okay, that's it. Thank you very much for your attention. If you have any question, please don't hesitate to contact us. Thank you very much.